Hi, everyone. My name is Jesse Barnes. I work as the technical lead for the Chromium OS kernel group and also manage part of the team directly as well. So today I'll be going over the Chromium OS kernel, what our mission is overall, some of our strategy to achieve that, some projects we've got going on. We've got a lot of really interesting stuff, and some of the metrics we use to measure our progress. So let's jump into it. Depending on how quickly I go, there may be plenty of time for questions. So please use the link to add any questions you have in real time, and then I'll try and get to them at the end. So anyway, onto the mission. So the goal is pretty clear. We want to create a stable and secure and high performance foundation for Chromium OS. And Chromium OS, initially was built around web apps and Chrome. But of course, if you've been following it at all, you know that it's expanded quite a bit. Now we've got an Android runtime, we've got Crostini, recently launched Parallels. So we've got all sorts of other application and system level software that we have to host on the operating system beyond just the browser. And that has implications for the kernel development as well as the rest of the operating system. And then there are a couple key things that we want to get out of the kernel. So one of our primary goals is to really scale to a lot of different devices. So the Chromebook ecosystem is very complex. There are a lot of different SoC vendors involved. We've got ARM and x86, two variants of x86, of course, and multiple ARM vendors. So we support multiple architectures and a lot of different capabilities in these different SoCs. So when I say scaling, that means that we don't want the team to grow linearly with the number of devices that we have out in the field. We need to be kind of more of a logarithmic curve, and we want to be able to support them well. And so that means building out tooling and operating system support to allow that to happen. We also, and this is the part that people tend to get really excited about, or at least a lot of engineers, develop new technology. So, new SoC vendors are coming to us. We're partnering with them, developing new technology. Sometimes we develop, platform independent technology in the operating system. And we want to support these new use cases, whether it's Android or Parallels or what have you. And we want to take existing platforms and make them better. The Chromium updates allow this to happen in a really nice way. So that's another key element of the mission. And then finally, because we're an open source project and we're based on a number of big open source projects like Linux, on the kernel side, we want to work closely with Upstream on our goals. And so a lot of the team, work very closely with Upstream kernel developers. We're big contributors. We are a big member of Upstream kernel development. And so, we help kind of bring our perspective to the Upstream development. And one element of that is fast and frequent uprev of our kernels. So someone pointed out this quote at the bottom to me a while ago, and I thought it was a little bit funny because it's so kind of ambitious, especially relative to where we are today, that we're going to upgrade the kernel, right away when a new kernel comes out. Now, it turns out that's a huge amount of effort, especially, depending on the platform. We may have a large backlog of patches that aren't upstream, or a small backlog. We may have, highly tuned performance in some cases that we have to replicate when we upgrade the kernel. We have to deal with upstream regressions. So this turned out to be very ambitious and maybe a little naive back in the olden days, but it's still something to keep in mind. So I'll touch on that again later. So kind of walking through some of the pieces of the mission. So stability and security are obviously critically important, and you can't have a platform if it doesn't work for you. It's not going to be very useful. So these are some of the things that we focus on for the stability and security of the system. So clearly, we've got a lot of bug tracking and bugs that go on. A lot of you will find that as you're using Google applications that they'll ask you for feedback or ask you for ratings, and we do look at that stuff a lot. So a lot of times those get converted directly into bug reports, and engineers go attack them directly. So that's a really key part of our infrastructure. We also get crash reports on a regular basis. And the crash reports are like fairly high volume because we've got a lot of users out there, and they come from all different applications. And so we're always looking for, kind of data mining that to figure out where we've got fragile spots where we need to spend time to make things more robust, in future updates. And then we're always improving that system as well. So some people on my team are working on that to kind of give us better indications earlier about problems that may occur on, say, a specific platform. A key element is obviously testing, and especially on the upstream side, outside of Chromium, this is something that we're really interested in, and that's highlighted in that kernel CI piece. So we work closely with the upstream kernel CI developers on expanding that infrastructure. So we've been putting a lot of Chromebooks into that kernel CI infrastructure as an example. And we're also going to be working on putting tests into that infrastructure that are important for capturing bugs that people find on Chromebooks with Chromium OS. So the idea there is that the next time we do an Uprev, next time we pull a new kernel, it'll already be in good shape. That's the goal. And beyond that, we've got a bunch of fuzzing that goes on. So this is really key for stability and for security. So we're expanding our on-device fuzzing, and this is a really interesting project to me because it means we're fuzzing driver interfaces directly on real hardware, as opposed to a lot of the fuzzing that's occurred thus far, which tends to be system call focused and occurring in a virtualized environment because it's easier to recover from the errors that are caused and collect the data. So we're actually doing this on real devices as well and collecting and finding a lot more issues. The tasks and auto tests, those are things you'll find in the Chromium source repo. So those are the frameworks that we use for developing new tests and running our tests. My hope is that we'll be able to pull some of those tests out, or maybe make the task environment work in kernel CI or something like that, so that we can get some additional test coverage for upstream using the tests that we have that really leverage Chrome in our infrastructure to find bugs. One big element of the security piece, especially, and to a lesser extent the stability piece, is the fact that we track the long-term kernel releases really strongly. So when we choose a kernel for a device, we'll choose a long-term supported kernel from upstreamkernel.org, and whenever a new stable release comes out, we'll merge it in to our tree. So we'll pick up all the latest security fixes and all the latest stability fixes that way. It's a lot of work, but it's definitely worth it. And then finally, that Uprev piece that I talked about. So we'll periodically update platforms to a new kernel, new base kernel, in order to pull in the features and stability improvements and other security fixes or things that may be too big. So when I get to the project section, you'll see what I mean. But there are a lot of times we'll have a feature or some fix that's like somewhat invasive, or maybe it touches a driver plus the higher level stack, like a graphic stack or something. And an Uprev is a better place to pull that in than to try and backboard and manage a huge set of patches on top of an older kernel. So on the Uprev side, our goals are a little, we're taking a stepping stone approach there. So rather than being 3 to 6 months out from a new kernel release, the idea is that we want to shoot for every device every other year, and kind of continually reduce the time it takes to perform that Uprev. But the mindset that we have in Chromium is to imagine what it would take to take Linus's tree and just build it and ship it directly, right? Can we get to that point? I mean, a lot of, you look at big cloud vendors, Google, Facebook, and others, and they kind of do continuous release, right? And that's because they have infrastructure to roll things out slowly, catch problems, roll back aggressively. And I think that's the right mindset to have, even for shipping the base OS. And obviously, we're a long ways from having the capability or the test coverage in particular to make this possible. But I like to think about things that way. And so if we're missing some key performance metric and upstream regresses it, and then we pick it up on our next Uprev, we should be adding something to kernel CI to fix that. so that Upstream can detect it when people are landing patches and sending their pull request to Linus. Another couple pieces we have there are the backlog. So, obviously we've got time constraints. We've got to ship platforms on a specific time frame. We've got release dates. And so we have to land stuff and get it ready for people to actually use. And so we often land patches that don't go upstream, or maybe they don't go upstream right away. And that's our upstream backlog. And so that's something we just have to kind of be constantly vigilant about. And it's common to any open source downstream project. And it has its ups and downs. So that just requires a lot of work on our part. The test coverage I touched on already, and then the upstream quality is related to that as well. So I think both of those need to improve significantly for us to speed up and deliver higher quality uprevs. And it ties into our scalability as well. So if we're gonna be able to support lots of devices and stay current with the latest features that Chrome is deploying and the other pieces of the stack are deploying, we need to be able to upgrade their kernels quickly and easily. And so that's tied to the scalability to high device counts. On the performance front, so this is also kind of maybe more fun than thinking about stodgy stability. But this touches on some of the projects that I think are really fun that the team is working on the performance front. So I don't know if anyone has ever taken their Linux device or their Chromium OS device and run ps-elf while they're running a Chrome app, a web app. But there are a lot of threads and a lot of processes involved on a modern OS. So attacking kind of the scheduling piece of things is a really key part of our team's mission right now. So it's not just like the multitasking aspect, right? You have lots of tabs open, or you might have an Android app and Chrome going, or a video call and docs. But it's also about just the architecture of the apps themselves that are highly multi-threaded and multi-process. So there's a lot of moving parts there. And then there's security elements too. So the first big one, and this is a really big one, is the core scheduling project. So this is a project to update the Linux scheduler so that we can securely re-enable hyperthreading in light of the Spectre and other side channel based attacks. And that requires invasive changes to the scheduler, but it's really important because you need to get back that performance that hyperthreading gives you, especially when you have so many threads you can run. So that's a really big piece of the puzzle that we're working on right now. We've got big.little architectures that we support, and there's just more coming. And so you've got a mix of kind of big, high power, fast cores and a bunch of small cores. The size and capabilities change for these things over time, and the roadmap, has a bunch of new stuff coming. So it's something that we need to work on tuning and develop and improving our methodologies for, figuring out where threads belong, big or little, fast or slow, which capabilities they need. Are they latency sensitive? Things like that. The other element of like being highly threaded and highly process driven is IPC. There's a lot of IPC going on in Chromium, and the lower we can make the overhead for those individual IPC messages, or if we can bundle up IPC messages and kind of send them across all at once, that's huge. So that's another key thing we're looking at. And then there's a bunch of kind of smaller topics that like some of the tasks that we have on the operating system, like our audio server called CRAS, they're really isochronous, right? They need periodic time on a regular basis to make sure your audio doesn't skip, or the video decode in your conference call. So these are things where we can apply real-time techniques, and so we're kind of working on our infrastructure to improve those things. Memory management, you can imagine, would also be big, especially if you've got like a small device, maybe it's only got 2 gigabytes of memory. You want to make sure that you've got the right stuff in memory at any given time to give the best user experience. So we want to degrade gracefully. We want to have the right stuff in memory. So that's a really key part of our efforts as well. So we've got a few different efforts going on here. Like the user level swapping one I find is really interesting. So today, if you look at the kernel, it'll kick individual pages out of memory as memory gets low, and it'll write them to swap. And today for us, that's ZRAM. So we dedicate a portion of memory where we compress the pages and write them out to ZRAM. And that's slow for a couple of reasons. One, it takes a little bit of your CPU to do that. And it's just doing it a page at a time. So the kernel doesn't have good visibility into what the whole app is doing or the whole system is doing. So user level swapping allows us to kind of bypass that and put that intelligence up into Chrome or other frameworks. So in Chromium, you might have a memory pressure notification, which gets to that second bullet that says, hey, the system's starting to run low on memory. And Chromium has a good idea of what's going on. And it can say, oh, these tabs are not visible. Let's just write those out to disk. So user level swapping gets us that. And the advantage is Chromium can free a whole chunk of memory at a time instead of just one page at a time. It can write it out in kind of a higher performance way than if we added a block device for kernel swapping, for example, because it can do a big bulk write. And it can more smartly manage the page in and page out. So that's a really kind of key thing that we're excited about. The app level monitoring, this is, like I said, kind of pushing more of the logic for monitoring system state up into the applications that care about it, so they can kind of preemptively take action rather than relying on the kernel, which is kind of a big hammer, a very coarse-grained solution to like a low memory situation or out of memory situation. So that's also a really interesting piece of things. When the kernel does have to do stuff, we have some important features like kstld, which is the stale page daemon that looks at the memory activity and figures out which pages really ought to be kicked out or pulled back in. And it's much lower overhead than what you see in the stock kernel. So we're working with Upstream to try and figure out how we can get that low overhead and kind of smarter approach to work there, whether or not it uses kstld. And then we've got some kind of per process, like I mentioned the whole process knowledge about how applications behave and how they can make smarter decisions. So we have some of that in Chromium today, and we're pushing that into the Android runtime as well. So we can save some more memory, especially if you're not using Android at the time. It can have, it can take a lot of memory, and so if you're not using it for a while and you can just flush out whole chunks of it, that's better than having the kernel kick out one page here, one page there. So there's some other kind of, this is a little more high level performance level work, but I mentioned all of the different SoC types that we support, and then kind of the complexity of just platforms in general. So there's a lot of work that goes on there too, and it's less platform independent than the work that I just mentioned on the previous slide, but it's no less important, especially for the experience on any individual device. A lot of my time recently has been spent on video conferencing optimizations, and so I've put those in here. So the camera is very interesting. We have a couple different kinds of cameras on these devices, MIPI and USB, and they have some different overhead characteristics, and we're trying to reduce those. On the audio front, there's a whole bunch of stuff going on. The Sound Open firmware project, that soft that I mentioned there, is really interesting, and that can get us some additional capabilities, especially as the DSPs become more powerful. You can do things like beam forming or echo cancellation in the DSP instead of on the CPU, and free up some cycles for your applications. So those are pretty cool things. And then on the video front, we're always looking to offload that. Well, actually, there's a trade-off there. We want to offload that, especially if you're watching like a YouTube or Netflix. That's a very low power way, and you can get a nice long battery life, a low power way of watching video, having a dedicated hardware engine decode it for you. In the case of like video calls, it depends on the size of your screen and how many tiles you've got on the screen. If you're like in a classroom, if you've got a bunch of small tiles, it may be more efficient to do those on the CPU. So those are the kind of trade-offs that we're looking at on the video front all the time. As far as the tooling goes that we use for this, we use a lot of perf. That's just the open source Linux tool. And then on specific platforms, we use specific vendor tools, like on Intel's vTune and Sockwatch. And those give us a lot of additional information and insight about power and platform specific behavior, like memory bandwidth consumption. So moving on to the kind of metric side of things, how do we measure success? I mentioned the Upstream backlog. You'll see a slide on that. that's a key metric for us. So that's something I kind of remind the team of every month, how we're doing in terms of our upstream backlog, and what seems to be spiking or what needs attention. We also look at upstream contributions. I know some companies, will pay people or rate people based on the number of contributions that they do upstream. We definitely don't do that, but at the same time, it's important to kind of encourage people to get engaged upstream and at least think about it when they're developing something. So we do look at that, but yeah, it's not a matter of patch counts or line counts or anything like that. And then the crashes, definitely that's a piece of it. I mentioned about the crash triage. So looking at the crash rates on different platforms and figuring out, what's acceptable, what's kind of background noise based on hardware failures or other things, versus what are real issues when something spikes. That's a key metric for us. And then on the performance front, we have a number of metrics. So some of those come out of the benchmarks in the TAST and auto test that I mentioned, and others are actual user population metrics that we look at and monitor. So here's an example of what I use for the backlog tracking. So periodically we'll do these kernel uprevs and rebases, and at that time we get a really good handle of the outstanding set of patches, and then we track that over time until the next uprev occurs. And so on this one, I've taken our data and stripped out the stuff that is that's queued in the maintainer's Git tree, or that's already upstream, and just left the stuff that is worrisome. That's the Chromium patches and the from list patches, and to a lesser extent the queued patches. So the way we define this, if you look at the Chromium kernel tree, you'll see all of the patches tagged with some metadata. The Chromium tag means that it's Chromium only. It's not going upstream. It's not intended to go upstream, although the engineer should have a plan for how they upstream it. It may look different than the patch they've landed. Or in some cases, it's like not a backport, but something that's equivalent to something else that landed upstream, just we had to do it a different way for whatever reason. So those are the ones that are kind of most troublesome from a backporting and security perspective, because as we land the long-term stable kernel patches into our tree, those are the ones that are maybe more likely to conflict. And they also can be tougher to uprev. So you can see a lot of those red bars. Now the scale over here is not too bad, right? You look, okay, well, media, it's up above 40 patches, but really it's not like we're talking thousands of patches here, which is a good thing. And so I want to keep pushing the scale down. Ideally, we'd only see 0 to 20 here on all this. But you can see there are a few different pieces like VirtIO. The graphics team does a lot of optimization on the virtualized graphics interfaces between the VM and the host. So that's a kind of fast-moving piece. So we see that go up and down, which is fine. I pulled out a couple of the things that are kind of long-term Chromium patches that'll eventually disappear because of various features that we're pulling in or pushing out. And then you can see like a couple of the others that like cross EC. This is another area that tends to churn a lot as we bring in new platforms. We've got new sensors, and those touch the EC side of things, or we do new EC interfaces on a given platform. So those ones, they go up and down, but the overall age of those patches tends to not be super high. So finally, on the upstream side, we have a couple of things that we really that we focus on to help improve our upstream backlog, make it easier for us to work with upstream, and make it easier for us to send reports and results and bug reports to upstream with current code. So one of the things we've got internally, sorry, not internally, this is in the Chromium tree, in the kernel tree, is a continuous rebase branch. So what that is that's like the latest release from Linux, the latest RC or stable release, RC or major release, with all of the Chromium patches backported on top. Now, you can imagine that doing that might be tough across, a couple dozen platforms, and you're right. So it doesn't necessarily boot or run or have full features on all those platforms, because we might have to drop some Chromium patches just to, it's like usually a couple-day effort that we spend to update to the next RC. And so we'll kind of aggressively drop stuff. But this is a really nice tree overall because it allows you to, if you're working on something that also needs to go upstream, you can just pull down the continuous rebase branch, put your patches on top, do your testing, and work with the upstream community on getting it incorporated because you're using the same code they are. So that's really helpful. Or if we need to run benchmarks and report something back to upstream to justify a point or to provide feedback to someone who's providing a feature that may be interesting to us. So it's a really kind of key piece of our upstream development puzzle. And as we drop our upstream backlog, it'll get easier and easier and better and more stable. But it's kind of the other half of it is the kernel CI part that I've talked a lot about already. The more stable upstream is on Chromebooks and other Chromium devices, the better off we are with the continuous rebase branch, the better off we are when we have to upgrade the kernel. So we invest a lot there as well. And so these two things are coming together as we drop our backlog and increase the upstream quality. So there's a lot of work going on there. So with that, brings us to the development resources. I realize these links are not something you can click on. However, this is the kernel development doc from the Chromium tree. And then this is just the Chromium kernel repo. So those are the two kind of key upstream resources that everyone relies on. And especially if we have any like kind of new kernel developers, new Chromium kernel developers, I highly encourage you to check out that kernel development doc. And you only get to be new once. And so if you find issues with it or think of, have a tip or a workflow that is not covered in there and that you find useful, definitely submit a patch and we'll get it rolled in. So that tends to capture a lot of really good information. And the source repo, of course, is where we all play. So with that, I will check on questions. All right, well, I guess unless anyone wants to add questions, that's pretty much all I've got.